Now we're going to derive one of the two major types of methods for initial value problems. The idea is to go past the accuracy that Euler gives us. So what we'll do is we'll start with the ODE that we're given. So du dt is replaced by f of t ut. Now I'm doing this in Mathematica as a rule, and if I differentiate both sides of that rule with respect to t, so the left side of course is u double prime, but the right side, you see I have a function f that depends on two variables, t and u, but each of those depends on t itself, so there's a chain rule. So looking at this term first, this is the partial derivative of f with respect to its first variable, which is t. This is the partial derivative of f with respect to its second variable, which is u. And then there's an additional u prime for the chain rule in that term. So if we now look at what happens with u at a future time step, so let's say we know u of t and we want to find u of t plus h based on that, well, then we have a series expansion. So we'd have to get this much correct in order to get second order accuracy. All right, and what we'll do is we will replace all the derivatives of u with these rules that come from the ODE. So in other words, here's where we apply knowledge of the ordinary differential equation. And now all the u primes are gone and replaced by f's. Okay, so in order to approximate this stuff here, either we need to take derivatives of the f on our own and code those up, or we need to replace them somehow. Now one thing we could do is we could replace each partial derivative by a finite difference. That could work. It would require us to evaluate f 3 times to do one time step. And we're always trying to minimize evaluations of f. It turns out there's a way to do it with just 2, and that's what we'll do next. So here is the first evaluation of f that we're going to do to take our time step. Okay, it's the one that we always do. It's the one we do for Euler's method as well. All right. Now we're going to take a temporary step. So this, for example, right, would be the Euler's method if a1 is equal to just 1. But by putting a constant a1 in there, we can give ourselves a little bit of freedom. So what I'm defining here is a temporary value for the next time step, a temporary value for the next solution, all right? And then I will evaluate f a second time at these temporary values. So let me go ahead and do that. So we have this nested mess, okay? And then what we'll do is I'll use those two function evaluations for my time step. So we'll take u of t plus h times, not just the function value, but the combination of those two function values. So I've introduced these four constants, c1, a1, b1, and b2. They're unknown, and I'm going to use those to get second order accuracy. So if I then look at the difference between the exact solution at the next time step and the numerical solution that I just derived or just defined, I'll take the series of that difference up to second order. So I need to make the first 3 terms of this series. Whoops, I forgot to evaluate this one first. That won't work very well. So let me do that now and redo this. Okay, so I need to make all these terms 0 up to order h cubed. So I need to make this term 0, and I need to make all the rest of this 0 as well. And then I'll get second order of accuracy. So what I'll do is I'll peel off the coefficients of different powers of h. Okay, the first one is 0. The coefficient of h to the 0 is 0, so I don't need to do anything. That's already taken care of. Coefficient of h to the first power, okay, is that. So if I make this equal to 0, right, then I will have satisfied that that term is equal to 0. So let me set up an expression for that. And then we'll look at the h squared term. Okay, there's a lot there, but really, if I set this equal to 0, that gets rid of the first term. So I'll call that order 2a. And if I set this one equal to 0, I get rid of the last term, regardless of what f is. And I'll call call that order 2b. Oops. Okay, so now all I need to do is to solve these three equations. Okay, these three conditions will be 0, and I have these 4 variables to do it. So we get this little note, and of course, because there's only 3 equations and 4 variables, it's not surprising that there's more than one solution. All right, let me actually call this RK2. So for instance, so if I pick a value for B2, then everything else is determined. So if I look at RK2, where I let B2 become, let's see, what do I want B2 to be? Let's let B2 be 1. Okay, so that's one method. And I believe we call this one the improved Euler method. Or we could do it where RK2 is equal to a half. I'm sorry, where B2 is equal to a half. Okay, we get another method. So really all these methods in a way are pretty much equivalent. They're all second order accurate. And RK stands for Runge-Kutta. These are German names, so it's not Runge, it's Runge.